Good afternoon. We'll be starting on DC motor starting, braking, and speed control today. So I'm going to first start with how the DC motors are started, what are all the normal problems with starting, and how we are going to overcome those things. That's what we are going to look at today. Okay. So, when we look at the starting of a DC motor, generally, if we are writing the expression for the armature current of the DC motor, we wrote it somewhat like this. This is VA is the applied armature voltage and EB is the back EMF. So VA minus EB divided by RA is going to be the armature current drawn by the DC motor. When we are starting, during starting, we are going to have speed equal to 0. So in the beginning of starting, speed is going to be 0. So if speed is 0, EB is proportional to omega m as well as the flux. So even if we keep full excitation, the back EMF is going to be 0 when speed is 0. Because the back EMF is 0, we are going to have IA during starting that is going to be equal to VA divided by RA. And if you look at a typical rating of a DC motor, what we use in India, most of them are working at 220 volts or 230 volts. And if we are talking about, let us say, a 2.2 kilowatt motor, we are going to have the current, armature current rated value will be of the order of 11 or 12 ampere. Okay. So in which case, you can say if 12 ampere is the rated current, generally back EMF is going to be approximately equal to VA, which is 220 volts itself. So IA-RA drop will be only about 5% of whatever is the applied voltage. That is the reason we are able to neglect it and we can say EB is approximately equal to the applied voltage. So RA is going to be generally about 10 to 12 volts. I mean, the drop is going to be 10 to 12 volts, which means RA is going to be close to 1 ohm, nothing more than that. So if you imagine RA is 1 ohm, 220 divided by 1 ohm, the starting current can be as high as 220 ampere, which is really, really large. So if I have to plot this and show you exactly where the corresponding torque is lying in the torque speed characteristics, if I say this is TA, TE, and this is the speed that we are talking about. So if I say this is speed, so in that case, normally we drew the characteristics somewhat like this. This is how the normal characteristics is. So you have to extend it in such a way that it meets with the zero speed portion. So I have to extend this also as a straight line. So you can see that this will be the operating point corresponding to RA, whatever is the inherent value. And if I apply rated voltage, if I'm going to apply rated VA with rated excitation, I'm going to have a very, very large torque or very, very large IA value. So IA value as well as TE value, both are going to be extremely, extremely large, which means I'm definitely going to have the fuse blowing. The commutator will not be able to handle this kind of a large value of current during starting. That is the reason why generally we adopt something called resistance starting. So one of the starting methods for a DC motor drive is resistance starting. So what do we mean by resistance starting? So what we are going to do is, if it is a separately excited DC motor drive, I'm going to have the armature like this. To the armature, I'm going to connect multiple resistances in series. So I'm showing 4 resistances here which are connected in series. And each of them is going to have a switch connected. So this switch will be closed once the motor picks up speed to certain extent. So these switches will be closed sequentially. So if I may call this as R1, this is R2, this is R3, and this is R4, and the inherent resistance is RA. Let me call this as S1, S2, S3, and S4, 4 switches. So I'm having 4 steps of resistances here along with the inherent RA to limit the initial starting current. So if I'm going to apply VA as the initial voltage across the armature, I'm going to have VA divided by R1 plus R2 plus R3 plus R4 plus RA. All of them put together, that is going to be the starting current, what I am looking at in terms of the motor, that is what it is drawing during starting. This is what we mean by limiting the starting current using a resistance or using a set of resistances. So if I am looking at the speed torque characteristics now with the increased value of resistance, I may have the speed torque characteristics somewhat like this. This is going to be the speed torque characteristics. If I may call R1 plus R2 plus R3 plus R4 plus RA as, let us say, R4 dash. Totally, I'm calling this as R4 dash. So this characteristics is going to be corresponding to R4 dash. And I can say this is the electromagnetic torque axis, and this is going to be the omega axis. And when I'm looking at omega equal to 0, this point, then I'm going to have this as the current drawn. And this is going to be the electromagnetic torque produced, because in a separately excited DC motor, TE is going to be proportional to IA if flux is a constant. If flux is a constant, then we are going to have TE and IA are proportional to each other. So let me call this point as I max. Maybe this is the maximum current that can be withstood by the motor. Now, this corresponding to this Imax, there is going to be an electromagnetic torque developed. Because the electromagnetic torque is developed, there is going to be acceleration of the DC motor drive. You are going to have J d omega by dt equal to TE minus TL. Now, if I am going to have a good amount of electromagnetic torque developed as compared to the load torque, then I'm going to have a sufficient amount of acceleration that is taking place in the motor drive. So the speed is going to increase like this. And let us say at this particular speed, when it has reached this particular speed, maybe the back EMF is something like EB1. So this is going to be the back EMF at a particular speed. So corresponding to that, let us say the current what I am getting here is I minimum. So I want at least a minimum amount of torque to be developed during the starting process. So I'm going to allow the current to vary only between I max and I minimum. I max, the limit is set based on what is the value of the current that can be commutated successfully by the commutator. So this is going to be I max and this is going to be I minimum. Okay. Now this has reached this particular EB value. So at that point, I'm going to cut off one of the resistances. Say I'm going to cut off this R1. So when I am cutting off R1, what I have is only R2 plus R3 plus R4 plus RA. Let me call that as R3 dash. So the next characteristics that I am looking at, that is going to be corresponding to R3 dash. So this is R3 dash. This is corresponding to R3 dash. So from operating point, initial operating point, let me call this as A. From A, it is going to migrate to B as the motor accelerates, and then it is going to migrate to C as the motor is operating at a resistance of R3 dash rather than R4 dash. After cutting off R1, this is going to be the operating point. Now, after this, again, you are going to see that the machine is going to accelerate along this direction. So this is going to be from C, it is going to reach a point probably D. So this operating point is going to be D. So once it reaches D, operating point D, now again you are going to cut off one more resistance. So when you cut off one more resistance, that is this R2 is going to be cut off by closing the switch S2. So what is going to happen is now again, this will travel along this direction. So from D, it is going to travel towards E. So once it reaches E, it is actually corresponding to the resistance, which is only R3, R4, and RA. So I'm going to have R3 plus R4 plus RA. That is going to be equal to R2 dash. So this is R2 dash. So I'm going to have a characteristic somewhat like this. So I have to join this point. If I may call this point as O, O and E needs to be joined. These need to be joined. So this corresponds to R2 dash. Now from here, again, there is going to be acceleration. So because of acceleration from E, it is going to travel towards F. So this point is F now. This point is going to be F. So once it reaches the point F, the minimum current has already been reached. So I have to cut off the next resistance also, which is R3. So I'm going to have R3, R4 plus RA. R3 is eliminated. So I'm going to have R4 plus RA, which is going to be equal to R1 dash. So from here, the characteristics would travel towards this. So this point becomes G, and the traveling direction will be from F to G. So from F, it has traveled to G. So previously it traveled from D to E, then E to F, and F to G now. Now from here, again, I have to draw another characteristics like this. So this characteristics now correspond to R1 dash. This is going to be corresponding to R1 dash. So again, there will be an acceleration in this direction. So from G, it has to travel towards H. So this is going to be H. This point will be H. Okay. So H is the point which is corresponding to again I minimum. So after that, I may cut off the last resistance, which is R4 also. So this characteristics may be the natural characteristics which is corresponding to RA. So let me write these back EMF points also. D and E correspond to the back EMF, which is EB2. Similarly, F and G correspond to a back EMF, which is EB3. And finally, from G, it would have, from F, it would have traveled to F and G, then H. Then from H, it will travel to probably I. So I should have one more back EMF point, which is corresponding to this point. So that is going to be EB4. So let me try to write the equations now. I can simply say that VA divided by R4 dash is equal to IA max. Okay. Then I can also write VA minus EB1 divided by R4 dash, which is corresponding to this particular point, which is corresponding to B. So this is corresponding to point A. whereas this is corresponding to point B. This is going to be equal to IA minimum. And corresponding to point C, I should be able to write as VA minus EB1 divided by R3 dash. This is the resistance. That is equal to IA max again. Right? And similarly, I should be able to write corresponding to point D, which is IA minimum. That will be equal to VA minus EB2 divided by R3 dash. So that is corresponding to point D. This is point D. You can see that this is point D. Then point E is going to be corresponding to VA minus EB2 divided by R2 dash. That is again IA max. So in general, what I can write is, if I try to write, for example, IA minimum divided by IA maximum. For example, I should be able to write this as VA minus EB1 divided by R4 dash. That is IA minimum. So I can write VA minus EB1 divided by R4 dash. And that is divided by VA minus EB1 divided by R3 dash. So I will have this VA minus EB1 and VA minus EB1 cancelling out with each other. So I will get this as R3 dash divided by R4 dash. The same way, when I consider this expression, VA minus EB2 by R3 dash and VA minus EB2 by R2 dash, they both of them correspond to IA minimum and IA maximum respectively. So this will also be equal to R2 dash divided by R3 dash. Similarly, I should be able to write this as R1 dash divided by R2 dash. And finally, it should have RA divided by R1 dash. So this will be the kind of, expressions that I will have. So I should be able to multiply all of them. So IA minimum divided by IA maximum whole power. So there are 4 such expressions. That is 1, 2, 3, and 4. So whole power 4, because this is a 4-step starter. That is going to be, when I multiply all of them, this R3 and this R3 dash will cancel with each other. R2 and R2 dash will cancel with each other. R1 and R1 dash will cancel with each other. So I'm going to get RA by R4 dash. If I may call this as R total or whatever. So this is the total resistance, which could limit the current to the maximum armature current value, which could be commutated successfully by the commutator itself. So this is going to be equal to RA divided by R total. So if I am given how many steps of resistances I am going to use, and what is the maximum current that can be commutated by the commutator brush assembly, I should be able to calculate what is the minimum current value to which the armature should be subjected to, and what is the kind of minimum torque the armature will be developing. And I should also be able to calculate each and every step of resistance, because R4 dash, R3 dash, R2 dash, and so on, I'll be able to calculate without any difficulty. So the starting of a DC motor normally is done in many of the cases by having external resistances inserted along with the armature. So most of the times what we use as the starting method is resistance starting. So when we are using resistance starting, series resistances will be connected with the armature circuit. And they'll be cut off slowly as the speed picks up. So the back EMF will build up and correspondingly the current will be automatically limited by the virtue of the back EMF increasing. So that is the reason why you would be able to cut off the resistances as the back EMF increases along with the speed. But excitation should be at its rated value. So you should have the excitation at its rated value. That is important. So this is specifically how the resistance starting works. But these days, what we try to do is to adjust the armature voltage. So the armature voltage is gradually increased. So in armature voltage starting, VA is gradually increased. So when VA is gradually increased, the speed also increases slowly. So if you try to look at it, you will see that initially you may have a very, very small voltage. So this may be the corresponding current that is drawn by the machine. So at zero speed, if I may call this as VA1, you are going to see that this is the kind of torque that is developed. And this is also going to be corresponding to the armature current, which is drawn during starting, which is very, very small. So the machine is going to slowly accelerate along this path. This is how it is going to accelerate. So this is point A, which is the starting point, and slowly it is going to accelerate towards B. So by the time it reaches some point B, what you are going to do is to increase the voltage to the next level. So the voltage might increase to the next level. So I may have another armature voltage characteristic somewhat like this. So let me show a parallel characteristics. So I'm going to have another parallel characteristics, one more parallel characteristics, and one more parallel characteristics, and so on. So this is going to be basically the characteristics of this machine. So from B, it will shift to, say, point C, because you are going to increase the voltage from VA1 to VA2. Then you may increase it to VA3. Then you may increase it to VA4 and then VA5. So this is going to be the speed as well as voltage axis, because if you look at speed and voltage relationship, EB is going to be proportional to omega at constant flux. That's why I can say this is omega or EB. Either way is fine. So now from B, it will shift to C when I try to change the voltage now to VA2. Now again, this machine is going to accelerate along this direction. So maybe it will again reach point D. So this is going to reach point D at this point. So now from point D, again, if I try to change the voltage to VA3, then it is going to reach a particular point which is corresponding to point E and so on. So this is going to repeat itself again and again. So you see that generally either by armature voltage control or by resistance adjustment, you would be in a position to start the DC motor without the current, armature current exceeding its limit. But in armature voltage, controlled armature voltage being applied to the DC motor, that requires either a rectifier, diode rectifier with auto transformer or tap changing transformer. So you might require auto transformer or tap changing transformer. So you are going to change the AC voltage itself that is applied to the diode rectifier slowly, either that way or you should have a thyristor rectifier, where you will change the firing angle slowly. So the firing angle may be changed from a larger value towards 0 degrees slowly. So one of these things will allow VA to be varied. So the armature voltage will be varied based on either a diode rectifier with an auto transformer or a thyristor rectifier with varying firing angle. So that is going to slowly change the armature voltage so that your machine is able to accelerate at a slow pace without the current exceeding whatever is the limit that is generally withstood by the commutator and brush assembly. So let me try to work out one numerical example for calculating resistances for starting a DC. Okay, so we are going to calculate the resistances for starting a DC motor. So let me take out the problem statement. So it's a 220 volts, 800 RPM, 84 ampere, separately excited DC motor. So this is the parameter rated nameplate details of the motor, and RA, the armature resistance, is equal to 0.120. Okay. And it's basically saying that the maximum current that can be tolerated by the commutator brush assembly, that is 200 ampere. Okay. So now if we are going to use a 5-step starter, if a 5-step starter is to be used, calculate IA minimum and the steps of resistances. So this is what is being asked. Okay. So to work out this problem, first of all, we need to say what is the total resistance that needs to be included. So it's the 220 volts motor and the maximum current that can be tolerated is 200 ampere. So PA divided by IA max is going to be R total. So this can be calculated as 220 divided by 200. So this corresponds to 1.1 ohm resistance. So this is inclusive of, because it's a 5-step resistance starter, I can say R1 plus R2 plus R3 plus R4 plus R5. This is going to be 1.1 ohm. Okay. So just to draw the, plus RA. Of course, I have to add RA as well. RA plus R1 plus R2 plus R3 plus R4 plus R5. That is 1.1 ohm. And RA is given to be 0.12. So I can say R1 plus R2 plus R3 plus R4 plus R5 is equal to 1.1 minus 0.12. So that will come out to be 0.98 ohms. So that is the total resistance that needs to be included. So I have to show it somewhat like this. I'm going to have R1, R2, R3, R4, R5, and then the armature connected here. Okay. So this is going to be R1, R2, R3, R4, and R5. And I'm going to connect VA voltage source here, which is 220 volts. And RA is the inherent resistance of this particular armature. Okay. Now, originally we wrote IA max divided by IA minimum whole power N. Here N is 5. So how many steps of resistances I have? That goes as the power. Okay. So that is equal to whatever is my R total divided by RA. Right? That's what we wrote in the last thing. If you may look at it, this is what we wrote. RA divided by R total here is equal to IA minimum divided by IA max whole power 4. That's what we wrote. So what I have written in the next page is IA max divided by IA minimum whole power 5. So from here, I can write this as R total is 1.1 and RA is 0.12. So I should say 1.1 divided by 0.12 whole power 1 by 5. So this 1.1 divided by 0.12 is equal to 9.1667. So from here I should say 9.1667 whole power 1 by 5 should be equal to IA max divided by IA minimum. And IA max is already given to be 200. So from which I should be able to calculate what is IA minimum. And IA minimum is coming out to be 128.41 ampere. So IA minimum comes out to be 128.41 ampere. So this is going to be the minimum current. Now, I should be able to calculate what are all the different values, something like R5 dash, then R4 dash, then R3 dash, R2 dash, and R1 dash. So R5 dash is consisting of, or R5 dash is same as R total. Whereas R4 dash is going to be, let us say, R2 plus R3 plus R4 plus R5 plus RA. So R1 is short circuited here in the second step. So this is going to be R1 plus R2 plus R3 plus R4 plus R5. And similarly, I should be able to write this as R3 dash is going to be R3 plus R4 plus R5 plus RA. And this is going to be R4 plus R5 plus RA. So the last one will be R5 plus RA and I will have only RA. So these are going to be the different steps of resistances. So I should be able to calculate this as IA max divided by IA minimum is going to be equal to R5 dash divided by R4 dash. This will also be equal to R4 dash divided by R3 dash. And this should be equal to R3 dash divided by R2 dash and so on. And finally, it is going to be R1 dash by RA. So this is the way it is going to work. So you should be able to calculate. We know R5 dash already, which is corresponding to R total, which is 1.1 ohm. This is corresponding to 1.1 ohm. And we also know RA. RA corresponds to 0.12 ohm. This is 0.12 ohm. So we should be able to calculate all the other steps of resistances without any difficulty. So corresponding to this, we are getting what are all the values of R1, whatever is to be closed first. R1, which is to be short circuited first. After starting, within a first few seconds, it has to be short circuited. So this is going to be R1. So that comes out to be 0.394 ohm. R2, which is to be short circuited next after R1. So that comes out to be 0.2526 ohm. Similarly, R3, which is to be short circuited after R2. So that comes out to be 0.16229. Okay. Then R4 comes out to be 0.10421. And the last step of resistance, R5, that comes out to be 0.0669 ohm. So the resistances in each of the steps can be calculated somewhat like this, from which we will be able to actually arrive at the currents are always remaining between IA max and IA minimum, and the commutator will be safe, and the motor will be able to develop at least a minimum amount of torque. So this is the way generally the resistance starter is divided for a DC motor. Now, let us look at the stopping process or braking methods. So braking is basically controlled stopping of a motor. So the control over a stopping process, that is generally known as braking. Okay. So why do we really need braking? If we are having an electric vehicle and we want to avoid accidents, in that case, braking will be extremely important. So if we are talking about a traction motor, if you are seeing a red signal, then you have to stop. So if you want to respond to traffic signal, then also it is important to stop the motor properly. Then the third thing very often that is needed is for comfort. So if a train is actually moving and you want to stop it exactly in front of the platform, you don't want to really stop it in the outer. And very often you might have seen that in many of the railway stations, they'll say carriage number 1 will stop at this point, carriage number 2 will stop at this point. So to stop the train precisely. So for making sure that for user comfort and also for stopping the train, a vehicle or a train exactly at a specified point. This is even required when you talk about robotic mechanisms. You might like to move an arm of the robo only by a few inches. So you have to stop exactly at that point. So in those cases, braking becomes extremely important because braking will make sure that the stopping is done in a controlled fashion. So there are mainly three types of braking that are employed for any kind of electric motor. For DC motor also, this can be employed. So the first and foremost type of braking is called regenerative braking. So in regenerative braking, what is done normally is the kinetic energy that is stored in the rotating parts of the machine that is converted into electrical energy by making the machine work as a generator. So the machine will work as a generator during this regenerative braking. And then it will feed the electrical energy back to the grid. So this may feed it back to the source, either to the grid, or if it is like a battery, to the battery, it will feed back the electrical energy. So here no amount of energy is wasted. Very, very minimal amount of energy is wasted. Only whatever is the IA square RA drop, which is taking place in the armature resistance, that is the only thing that cannot be retrieved. So that is going to be wasted as heat energy. But other than that, all the kinetic energy is recovered and it is converted into electrical energy and fed back to the source. So this is one of the most energy efficient forms of braking. So this is the most energy efficient form of braking. But to implement this, very often you may require some bidirectional converters. In most of the cases, you will need a BDC, which is a bidirectional converter. And the source should be in a position to accept the energy also. If I'm having a capacitor, it can get overcharged and it can be blown completely sometimes. So it is very important to have a bidirectional converter, and also source should be in a position to accept the energy. Regenerated energy or regenerated power. So regenerative braking, although is one of the most energy efficient forms of braking, it may not be very easy to implement it. That is one of the problems you might face. The second type of braking is called dynamic braking or rheostatic braking. So in dynamic braking or rheostatic braking, what we are going to do is, again, the machine will work as a generator, converting the kinetic energy into electrical energy. But this particular electricity is going to be dissipated, or this energy is dissipated in an external resistance. Only thing is the external resistance value can be adjusted as per our requirement, so that if you want to dissipate it really fast and stop the motor fast, you should be able to do it. But if you want to do it very slowly and gradually, that can also be done. So dynamic braking or rheostatic braking is basically wastage of electricity in an external resistance, but that can be done as per the requirement, whether you want a fast stopping of the motor or slow stopping of the motor. The third type of braking, which is known as plugging, this is called plugging. or reverse current braking. So what you are going to do is to connect the source in the opposite sense. So connect a voltage source with opposite polarity compared to the original polarity. So what is going to happen is a current will flow in the reverse direction, because of which a torque, a braking torque will be developed. So there will be a braking torque developed. So that is going to really stop the motor very, very fast. The braking torque value can be adjusted by adjusting what is the current that is being drawn by the motor in the opposite sense. So this will definitely stop the motor very fast, but you are not only wasting the kinetic energy, but you are drawing additional amount of energy from an external voltage source, and that will also be wasted. So both kinetic energy in the moving parts plus power drawn from the voltage source both are wasted. So when you apply a brake normally in a car, the mechanical brake actually puts an impediment. So if this is the wheel that is rotating, what you would see is basically you are going to have something like a belt which is going to be holding it tightly. So the wheel will not be able to rotate. So physically you are trying to put an impediment by putting a belt and then holding it tight. So mechanical brakes will always be stopping the machine with the help of some friction. So definitely there is going to be a huge amount of heat generated, and there is going to be wastage of energy. And one more thing you would see normally is there will be a lot of wear and tear. You cannot really, prevent these things at all in mechanical braking. Whereas in electrical braking, depending upon what kind of methodology you employ, you will have very good control over the stopping process. Not only that, you may be able to recover the complete energy also in the form of regenerative braking. So these are some of the methods of braking. Now let's start with regenerative braking. So what is regenerative braking? So in regenerative braking, if let us say this is my separately excited DC motor, and I'm going to have the field here. So when it is in motoring condition, I'm going to apply VA like this, and I'm going to have the current flow in this direction. This is going to be IA, and this is going to be IF. So I'm going to have the rotation in this direction. So this is going to be omega, and the torque also going to be produced in the same direction. This is going to be TE. And at this point, I'm going to have the back EMF, which is EB like this. And, this is opposing whatever is the polarity of VA. So during motoring, I am going to have EB less than VA. If let us say I'm talking about a motor or a vehicle which is moving down the gradient. So let us say the road is somewhat like this. It is coming down like this. Okay. So under this condition, the gravity is going to really pull the vehicle. So if let us say this is the car that I have drawn. Let me draw it properly. So let's say I have a car here which is moving down this gradient. So I'm going to have a couple of wheels and it is essentially moving down. So naturally, the gravity is going to pull it down, due to which the speed is going to increase. So if the speed increases beyond rated value, then EB can become greater than VA. So if EB becomes greater than VA, let me again draw this circuit. Okay, so I'm going to have plus here and minus here, and this is going to be EB. And here I'm going to have VA, which is going to be with plus here and minus here. So if EB becomes greater than VA, the current has to flow in this direction. So if the current is flowing in this direction, please note the armature current is going to be in the opposite sense compared to the motoring operation. So this is regeneration because armature current has reversed its direction. So if armature current has reversed the direction, whereas field is still in the same direction. This I have not changed at all. So I'm going to have the torque in the reverse direction. The torque is going to be in the reverse direction, whereas I'm going to have the speed still in the forward direction. So this is braking because the torque and speed are in opposite directions to each other. So if I try to show exactly how the characteristics are going to be, let us say this is TE and this is omega, which is also indirectly back EMF, and TE is indirectly IA. So the normal operating condition probably is something like this. So probably here the motor is operating. This is the operating point, which is corresponding to some P. Now, if the vehicle is moving down the gradient, then the speed is going to increase further and further. When the speed becomes greater than the nominal speed, so this is the nominal speed, this is the nominal speed at which it was originally operating. This is the no load speed. So if the speed becomes greater than the no load speed, this is going to be the operating point. So this is Q. So under this condition, you can see that both the torque and armature currents, both of them are going to be in the reverse direction. So this is reverse IA as well as reverse torque. So the speed is positive, but the torque is negative, because of which the motor will start slowly decelerating. So it will try to reach this point, but again it is going to come down somewhat in this direction. But please note, the moment it reaches omega no load, this particular point, then again the torque as well as the armature current, they are going to become positive. So it's not braking anymore. So if I am doing it with the fixed value of VA, the armature voltage, I would be able to bring it down only until no load speed, because below no load speed, again the torque as well as armature current will become positive. So if I really want to bring it down to zero speed using regenerative braking itself, then I should have a family of characteristics like this. Maybe this is one characteristic, this is the second characteristics, third characteristics, and fourth characteristics, and so on. So if I am looking at the entire functioning, and this is TE and this is omega, let us say originally my motor was functioning somewhere here. Okay, so this is the initial operating point. It will go along this. and it may, it would have reached some point like this. But rather than that, if this is the operating point and this original voltage was VA1, if I suddenly come down to VA2, let me extend this characteristics to the other side. So if I try to look at where this operating point is, corresponding operating point is, it has just reached the second quadrant. Or if I even bring it down further to VA3, it would have definitely reached the second quadrant. So from VA1, if the voltage is reduced, how we reduce is a matter of detail, but reduced to VA3, the operating point shifts from A to, it will shift to B. So this is going to be the shifting position. From A, it is going to shift to B. So B is in second quadrant. So that is the regenerative braking point. So now the machine will start decelerating along this particular characteristics. Now, the moment it reaches something like point C, again you can try to reduce the voltage to VA4. Then again this will shift from C to D. So I can say from C it will shift to D. So this is going to be point. So you would be able to have shifting from one point, or first quadrant to second quadrant, on a continuous basis by slowly and steadily decreasing the armature voltage. So you would see that the regenerative braking process occurs smoothly from rated speed or running speed to zero speed if we are able to vary the voltage or decrease the voltage gradually in the case of a separately excited DC motor drive. We will further continue with the braking process in the next class. Okay, so we'll be looking at the braking process in the next class. We will look at, first of all, regenerative braking of series motor drive. And after that, we will try to look at the dynamic braking and plugging as well.